When you have objects of like or opposite charges approach each other, they're either going to repel or attract each other. That shows that if they repel or attract each other, they're pushing or pulling, which means that there is an electric force involved. In this video, we're going to talk about that electric force, which is known as Coulomb's law. So here's a simple experiment. It's the amber effect that we talked about back in the first video, where if you have two objects of similar charge that are approaching each other, then they are going to repel and push it away, which means that there is a force. Well, what is that force? How do we calculate that force? Well, let's talk about some things that the force is proportional to. Well, first of all, we can look at the charges of the two objects. It doesn't matter at this point, it doesn't matter which charge is Q1, which charge is Q2. But the electric force gets stronger as either one or both of these charges get stronger. So the force is proportional to Q1. If you have a larger Q1, you're going to have a larger force. It's also proportional to Q2. And also there's a distance factor. If you bring the two rods closer together, it's going to push a little bit harder. So that means that there's an inverse relation to the radius, or the distance between the two. In fact, on further calculation, it shows that it is inversely proportional to the radius squared. And so if we put all this together, it turns out that all that's missing is a constant of proportionality, just a constant number. And so this is the equation that helps us to find electric forces, and this equation is known as Coulomb's law, where electric force is going to equal a constant K times the product of the two charges divided by the radius squared. And this constant K is 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. Two things I want to point out here. First of all, we've seen an equation very similar to this, where you have a force that is proportional to two masses, inversely proportional, and the force is inversely proportional to the square of the distance, and then you have some constant proportionality. This is Newton's gravitational law, and you see how similar these two are. Very similar. We're not going to go back and see gravity, but you could just see the similarities between the two rules. The other thing I need to point out is that Coulomb's law is for the magnitude of the electric force, which means that to be proper, I should really say absolute value. So electric force is equal to the absolute value of K times the product of the two charges divided by R squared. Here's what, let me show you. I'll come back to this in a couple of slides. Before I do, let me talk a little bit more about this proportionality constant. We use the letter K. However, we can also write it in terms of this number, epsilon naught, known as the permittivity of free space. You are going to see this constant at the end of this chapter and multiple times by the end of the section, and even into the next section. So this is a very important number. And this constant epsilon naught is equal to 1 over 4 pi k. So if you solve for k, then k is equal to 1 over 4 pi epsilon naught, which there's your k value right there. That's Coulomb's law. So you could use either method of Coulomb's law. The k value is probably easier to use at this stage of the game. But you have your value for epsilon naught right here, 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay, let's get back to this point about the magnitudes, that this electric force only gives you the magnitude. Now, here we are. Let's say that we have two positive charges. Then the electric force is going to be calculated as K times some positive charge Q1 times some positive charge Q2 divided by their distance squared. Well, then that gives you an electric force that is positive. Let me just write greater than 0 to indicate positive. Okay, that's the case that we have here in A, where you have two charges that are positively charged, and they push each other away, they repel. But we said that the force is positive, which makes sense here on charge 2 being pushed by charge 1 to the right. But if you look at charge 1 being pushed by charge 2, it's moving to the left. Shouldn't that be negative? But we calculated positive. That's why it's important to emphasize that Coulomb's law only tells us the magnitude of the force. And so when we get the magnitude of the force, we know how strong the force is, but we, through our intuition, have to say, oh, this is moving to the right, therefore it is a positive force. Whereas this charge here on F12 is going to be a negative force. And by the way, I want you to notice that these two forces are exactly the same. Why? Because if we look back down here at our electric force, what we've calculated is force of force on charge 1 by charge 2. So basically F12. But if I flip it around and I want to find the force on charge 2 by charge 1, then I just flip these two terms, flip the two terms around. Nothing's changed. The equation is exactly the same. So we see that these equal and opposite forces are just a manifestation of Newton's third law. To every action, there's an equal and opposite reaction. Okay, here in the figure, B is going to give us the same thing, only this time we have negative charges. Let me bring this back, so Q1, Q2. This time they're both negative, in which case you still have a positive charge or positive force because the negatives cancel out. But in the case for C, charge 2 is negative, but charge 1 is positive, which means you're actually going to have a negative electric force. So Coulomb's law, if you just calculate it and you get positives or negatives, then if you get a positive, that just means that your forces are going to repel. However, if your electric force is negative, then they are going to attract. That's all that the positive or negative in the electric force equation tells you, is if they're going to repel or attract. When you start dealing with multiple forces, you have to remember that this equation only really gives you the magnitude. The sign only tells you if it's attractive or repulsive. That's it. So we take the absolute value of Coulomb's law. So here's an interesting scenario where we have three charges. One charge at what we'll call the origin, another charge that is 52 centimeters away to the right, and a third charge that is 30 centimeters up above it on the y-axis. Okay, and so this charge on the bottom right is Q1, charge at the origin is Q2, and this charge up on the y-axis is charge 3. We're looking at the total force on charge 3. Well, let's start off with, oh, I just got rid of my pen. Let me start off here. The force by charge 2. Charge 2 and charge 3 are both positive, therefore they're going to be repulsive, And that gives us a force 3, 2, that pushes charge 3 away. And that's already drawn in here for you. We also have charge 1 down here on the bottom right. That's going to have an effect on charge 3. Charge 1 is negatively charged. Charge 3 is positively charged, which means that they are going to be attractive. So there's a force that pulls them together. And yes, it's in 2 dimensions, which means now we're dealing with a vector in 2 dimensions. We need to deal with vector addition. If you do not remember vector addition, you can go back to the beginning of chapter 3 in your textbook. I will also post a couple of vector videos just as a review for you to follow. So we deal with vector addition, and we end up with a total force that looks like this. And that is our vector sum of the 2 forces. Any net force on a charge is going to be the vector sum of all the individual forces acting on it. If we had 10 charges around charge 3, we could still find the total force on Q3 by adding up the force of all 10 charges on Q3.